We'll see an example of how to model motion and how to develop a free body diagram from a description of motion. So here we have an elevator that's suspended by a cable, and it speeds up as it moves upward from the ground floor. We are to draw a motion diagram, identify the forces, and create a free body diagram for the elevator. If we begin by drawing a motion diagram, our motion diagram shows the location of the elevator, and we're told that it's speeding up from the ground floor. So that means that it is at the bottom to begin with, and if it's speeding up, that means that at first it's going slowly, and if it goes slowly, that means that our points are close together. And if it's speeding up, that means that the points are getting farther apart from each other. And so this would be our motion diagram. And we can see that the velocity is initially very small. The arrow is very short, and so that means a small magnitude of velocity. And the velocity is getting bigger. The points are being more spread out as the elevator goes upward. We also know that if the velocity is getting greater as we go upwards, the acceleration vector is the difference. So the acceleration at 3, for example, is the difference between the velocity just before 3 and the velocity just after 3. And so we know that the acceleration has to be upward as well. If we are moving upwards and we're speeding up, that means our velocity is getting greater as we go upwards, so our acceleration has to be pointed upwards as well. Now, if we want to use that information to identify the forces, the first thing that we want to do is to draw a picture of the elevator. There it is, suspended by a cable. Now, presumably the elevator is in an elevator shaft, but we're going to imagine the elevator isn't slamming back and forth against the walls of the elevator shaft. It's moving directly up and down. And so what that means is then when we draw our line to focus in on the object in question, in this case the actual elevator, we look at what is connected to the elevator. We see that the elevator cable is touching our elevator, and so that cable will carry some tension. Everywhere else around the elevator is just air. We're assuming the elevator isn't banging back and forth between the walls, so we're not going to consider forces pushing inwards on the elevator or pushing outwards. And everything else around the elevator is air, and in this case we're going to assume that air resistance is negligible. Elevators move pretty slowly. Air resistance depends on the velocity, and so that's going to be a relatively small amount, especially in an elevator shaft where the airflow will be pretty small. The only other force to consider then will be gravity. Gravity is our long-range force, and we look at our long-range forces after we look at whatever forces are actually touching our object, like tension. And so here, the tension and gravity are the only forces acting on our elevator. The last step is to create a free body diagram of the elevator. And when we create a free body diagram, it's important that we have a single point. That single point represents the entire object, the entire elevator. We want to distill all of the complicated details of this drawing into the elevator just being a point, and we're looking at where the forces acting on that elevator will go. And we want to apply the forces that we've identified directly to our elevator. And so we will begin with gravity. That will be downwards. And gravity will be a fixed amount because however much the elevator weighs, that's how much gravity is. On the other hand, tension can be many different amounts. Tension is just holding up the elevator cab against whatever's pulling on it. But what else tension is doing here is going to be accelerating. The tension is pulling upwards, and that is what's going to give us the acceleration that the elevator cab is experiencing. And so it means that if we have a net upward acceleration, we need a net upward force. And so that means that the tension has to be bigger than gravity in order to give us a net upward force and a net upward acceleration. So when we draw our tension, we have to draw it a little bit bigger. And then what else we can draw is the net force. And what we see is that the net force should be the same size as the, actually that's not true. The net force should be in the same direction as the net acceleration, but the magnitude of the force and the magnitude of the acceleration will be different because they'll be scaled by the mass of the elevator cab. Here's another example of modeling motion. Here we have a skier that's being pulled up a snow-covered hill at a constant speed. We want to draw a motion diagram, identify the forces, and create a free body diagram for the skier. And so if the skier is going up the hill at a constant speed, we can kind of give ourselves an idea of where the hill is going to be, and then our skier is going to be going up that hill and now that we have the points, we can get rid of where the hill is. And so we see that the velocity, the distance between the points, is constant the whole way, and so that's how we have a constant velocity. If the velocity is constant, then that means that our acceleration will be 0 the whole way up, which is a big part of constant speed, is our clue that the acceleration should be 0. Now, if we want to identify the forces involved, we'll go ahead and follow our method of drawing the skier. There's the ski, there's a skier, and he is holding onto a rope going up the hill. And so, drawing the picture, now we're going to encircle our object. In this case, the object is the skier, and we're going to look at what forces are going to act in that area. So we have a rope that the skier is holding onto. That rope could carry a tension. The skier is standing on a surface. That surface could have a friction. Snow is pretty slippery, but it's not that slippery, and so you're likely to have some friction there. If you are on a surface as well, then there's going to be a normal force there that pushes up out of the surface, and then the rest of the skier is air. In this case, we're going to ignore air resistance because, again, skiers move pretty fast, but not hugely fast. We've looked at all the forces that act directly on our object. Now, the last one to look at are the distance forces. In this case, the skier is presumably skiing on Earth, and so there should be a force of gravity acting on the skier, which we write as mg, also as a capital W for weight. Now the last part, to find the free body diagram, we use a point to represent our object. In this case, it's a skier. We want to look at all the forces that are acting on our skier. We have mg acting directly downward. We have a tension, which we write as a capital T. We have a normal force that pushes directly out of the surface, and we have a force of friction. In this case, if we're moving at a constant rate up the hill, there'd be a force of kinetic friction. And so we identified 4 forces acting on our object, and we have 4 forces in our free body diagram. Now we see here you have 3 forces, actually normal force and the tension should be perpendicular to each other. These 2 forces are both acting against the tension. Normal force is acting perpendicularly to the tension, and so you have a component of the gravity that acts that way as well. We can go ahead and draw that. And you can consider a component of the gravity that is perpendicular to the surface and a component of gravity that is parallel to the surface. In either case, this angle theta that you see here is coming from the angle of the inclined plane, and when you add up all of these vectors that you see, the net force has to end up being 0. We saw that we're moving at a constant speed, so that means acceleration has to be 0, so the net force has to be 0. And when we draw these vectors, we have to draw them in such a way that they balance each other out to give us a 0 net force at the end.